Hello guys, welcome back to EC TechNest. In this lecture, we'll be discussing about the alternate circuit representation. There are three types of representation in the alternate circuit representation. First one is the behavioral one, in which you have to write the input for the given output. Next one is the structural one, in which you have to represent the components, and the third one is the physical properties, where you'll have to write about the dimension based on the lambda rules. So first we'll discuss about the behavioral one. F is equal to a plus b plus c dot d the whole bar. It's the OAI gate representation, and you'll write it as O3 and AI gate, because here you have OR operation between three variables. That's why we'll represent it as O3 AI gate. And next one is the sum. Sum is represented as a plus b, which is in the high level language. Now, in order to represent it in the form of conditional statements, we'll have to represent by taking if LO double equal to 1, then Q is equal to D. So in this we are putting a condition that is in the D flip-flop or latch. We are considering it if the input is 1, then Q is equal to D. So whatever value is present in the D, it will be stored in the value Q. Next is the data or the behavioral model. In the data or behavioral model, we'll use the assign statement. Assign statement will be represented by assign f is equal to not of a or b or c and with d. So this is the representation of this Boolean expression. It is the in the data flow model, but in behavioral model we'll be using case statement. Next is the structural description. In structural description, we will be representing it in the form of logic gates. And when you represent it in the form of logic gates, you'll not only use the AND or names, but instead you'll use the cell name. This you'll be learning in the laboratory of VLSI. So here I've used two AND gates. So the first AND gate name will be A1 and second AND gate name will be A2. Similarly, for the inverter, we'll represent using I1, and if there are further more inverters, we'll represent it as I2, I3 and so on. Similarly, for the OR gate, we'll use O1 and represent it in the form of a rectangle. After that, the output is mapped outside the rectangle and the final expression is written. And here input is also outside the rectangular box. This is the structural representation. So this is the CMOS circuit of a NAND gate. And next is we'll see how the N MOSFET and P MOSFET work when the input is given. So the first one, you'll write it as INV, that is the inverter of input. It is mapped to the output. After that, NFET. NFET has output, input and VSS, whereas P MOSFET has output, input and VDD. So this is based on the gate, source and drain terminal. Next, we'll represent it by the command end. So this is how you represent in the structural block. You have to write the convention. So the convention followed here is what is the value that is at the drain, next what is the value that is at the gate terminal, and next what is the value that is at the source terminal. So this is how you represent it. In NMOS, the drain terminal has output, that is the out, and gate terminal has input, that is represented as in, and source terminal has VSS. Similarly, in the PMOS, the drain terminal has out, gate terminal has in, and source terminal has VDD. Similarly, for the NAND gate, you have to represent it in the form of CMOS circuit, and then you have to follow the naming convention. The convention will follow drain, gate and source. Whatever values are present at the each MOSFET, that is the N MOSFET and P MOSFET, you have to write it. And this is how structural representation is done. So this is another example where it is the structural representation of a NOR gate. In NOR gate, we will consider two N MOSFET N1 and N2 and two P MOSFET P1 and P2, then represented in the form of a table based on the output and input values present in the drain, gate and source terminal. Next is the transient analysis. It is also called as the SPICE model. In SPICE model, it basically follows the lambda rules, that is 8 by 2 and 4 by 2. The ratio of PMOS and NMOS will be 2:1. Therefore, here it is in the ratio of 8 bar 2 divided by 4 bar 2. Finally, the ratio will scale down to 2:1. This is already in the simulator that you'll be using. This is the net list where we have VDD, Vin and M1 and M2. M1 and M2 represents metal 1 and metal 2. This you'll learn in the VLSI laboratory. And A is the input terminal, and we also have ground. In order to supply voltage to the circuit, we also have pulse. And W by L ratio is also important. For NMOS, W by L ratio is 4 by 2, and for PMOS, W by ratio is 8 by 2. This is based on the lambda rules. So this is how you write the transmission gate in the form of a model. That is part TG A, C, CB, and further map it to the output. These are the input values and these are the output values. Next, you represent the drain, gate and source terminal convention, and finally end the model. So this is how you represent it. Next is the representation of D-latch. So this is the diagram along with the symbol. In the previous lecture only I have explained the transmission gate model of D-latch. So next one is flip-flop. In flip-flop also similar to the model, you have to write the signal, the input and the output, and then you represent based on the number of inputs. As we are using two inverters in the D-latch circuit, here we have used two inverters, and then the input and output. So TG represents transmission gate. Next is the physical representation. In physical representation, we'll be discussing about the internal structure, how it is represented. So this is how it is represented. Here it is NMOS and here it is PMOS. Both are connected. This is something like the horizontal representation of the CMOS structure. Next is the layout design rules. Layout design rules are also called as the lambda based rules. There are many rules in the layout design rules. So it is mainly based on the lambda rules. So the color code convention is red for input, orange for PMOS and green for NMOS. And for power supply, the lines or the convention is dark blue line. So this is the NMOS structure and this is the PMOS structure. These are individual transistors. Individual O represents the orange color, R represents red and G represents green. This is the transistors having shared gate, and this is the transistors having shared drain or source terminal. So this is how you represent in the layout design rules. And lambda based design rules have the following rules. That is, minimum width of polysilicon should be 2 lambda and minimum width of the line should be 4 lambda and minimum width of metal line should be 4 lambda. So this is how you represent. Minimum width of diffusion line should be 4 lambda here. So this is how you represented it, and that's all for this module. In the next lecture, I will be discussing about the passing package and important questions in this module. Thank you.